This is the second lecture in our Chapter 5 look at the history of the periodic table. In this lecture, we're going to talk about the patterns and trends that we see in certain chemical properties with the organization of the periodic table. So we've talked about how the table is kind of like a map, and you can learn things about each element just like you would by looking at a map. You can kind of predict how that element will behave, just like you could predict the weather in a certain country by knowing where it is on the globe. So the first property that we're going to look at is atomic radii. So radii is the plural for the word radius, right? And so we're looking at the size of the atom across, right? The diameter is the atom across from one side to the other. The radii is half that distance, but the two measurements are basically, their patterns are the same. So the idea of atomic radii is just saying how big it is from the nucleus to the furthest energy level electrons. And that gives us kind of an idea of the overall size of the element or the atom. So as we're moving horizontally across the periodic table, so within a period, the radius of the atoms gets smaller and smaller. So on the left-hand side, it's pretty big, and on the right-hand side, it's relatively small. The reason for that is because when we are on the left side of the periodic table, there's usually just one or two electrons out here in this outermost energy level. And so they are kind of buzzing around doing their own thing. As we get toward the right side of the periodic table, there's a bunch of electrons all out here. And because they're more electrons carry more negative charge, that negative charge is more attracted to the positive protons inside the nucleus. And so the nucleus pulls that cloud more tightly, and it holds on to those electrons a little bit more tightly. And that stronger attraction makes for a smaller overall radius or diameter. So as we go across the periodic table, the radius decreases. As we go down in a group, so as we go vertically decreasing through a group, so from group 1, or pardon me, from 1 to energy level 2, 3, 4, 5, 6, as we go down, the atomic radius also tends to increase. So if we have, say, helium or hydrogen up here, as we get down to the bottom of this group, the size is going to be bigger because there's a lot more energy levels involved. And so think about this just like we've talked about our skyscraper building. As we add another floor, each level that we go down here, each new energy level, the overall building gets larger and larger. And it's the same thing with atomic radius. Next trend or pattern that finally, one of the last properties we're going to talk about is called electron affinity. Affinity means attraction to or interest in. So electron affinity describes how much an element would like to get more electrons, how much it desires to gain electrons. So there is a change in energy, which you know, right? Electrons are each found at a certain energy level, and when they move from one energy level to another, there's either energy gained if they go up a level, or energy lost if they go down a level. And so when we have electrons moving from one element to another, there's energy changing place there too. So the element that is gaining electrons loses energy, right? It has to basically pay the other atom to get the electrons, and it pays in energy. That's the money here. So when one atom takes an electron from another atom, it has to pay energy in order to get that atom. And so, or to get that electron, pardon me. And the reason that atoms will pay this energy is because it usually makes them more stable. Even that loss of energy helps them to become more stable. Remember, the ground state, or the lower the energy, the more stable the atom is overall. The group that has the highest electron affinity is the halogens. This is group 17. And they have they have 7 valence electrons, which means that their p block is almost full. All of the elements in this group have something p5 as their electron configuration, and they really want to have that p block be full. Anytime we can fill up any one of these sublevels, it makes the element more stable. An element that's S2 is more stable than S1. An element that has D10 is more stable than D9. And an element that has P6, the noble gases, is much more stable than an element that has P5. So the halogens really want to get an electron from another atom to get up to a full p block, to go from p5 to p6. And so they have a really strong affinity. They really, really, really want to take electrons anytime they can, because it makes them more stable and it fills up their outer shell. So halogens have the highest electron affinity in the periodic table. Every other group is less than the halogens, and it tends to, let me kind of shift this here. As we move through the periodic table, here we are again, so group 17 is right over here. Here is our highest electron affinity, and then as we move away, the electron affinity drops. So it's still relatively high in this area, but as we get across the periodic table, it's getting lower and lower and lower and lower. And over here, there's basically no electron affinity. The metals over here don't want electrons. They already have either S1 or S2. So they would much rather just give away those electrons so that they have a full p shell and then nothing beyond that, right? Because if they give away those electrons, then their electron count goes down and they end up being more like the noble gases. We'll talk more about that coming up. Trend that we're going to talk about goes right is the number of valence electrons that we see in elements in the periodic table. So valence electrons are the electrons that are in the highest energy level. So they are the least attracted to the nucleus. That's energy level. So they're the least attracted to the nucleus. So they are easily pulled away from the atom. It's easy to manipulate them, and therefore they're very involved in chemical reactions. Because of the way that energy levels fill and the amount of energy, we are only dealing with S and P electrons here. The D sublevel electrons are in a lower energy level. Remember, once we get up to 4S, then we fill 3D, then we fill 4P. So the highest energy level here is going to be 4S. It's going to be energy level 4. S and P, because the D electrons are down in energy level. They're not in the highest energy level, so they're not considered valence electrons. The pattern here is pretty easy, actually. So when you look at our periodic table, right, we've got sort of this structure. And we start with group 1 here, and then group 2, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then we pick up at 13, 14, all the way up to the noble gases, which are 18. So if we could extend, there we go. So the valence electron pattern follows the group number. But again, we're only looking at the S and P blocks. So here's our S block, here's our P block. So group 1 all group 1 elements have one valence electron. It's the S1. Remember, we talked about that in the last chapter. The group 2 elements all have 2 valence electrons. They're both in S2. Then we skip the transition metals because those are D block elements. Then we get over to group 13. Group 13 has 3 valence electrons. Group 14 has 4 valence electrons. 15, I bet you can figure out here, has 5 valence electrons. Group 16 has 6 valence electrons. Group 17 has 7 valence electrons. And group 18 has 8 valence electrons. So just by knowing or being able to identify the group number, we can know the number of valence electrons as well. And that will be really important in the coming start looking at chemical reactions. Electronegativity. So electronegativity is another description of how much the element holds its valence electrons, how tightly it holds them. So it tends to be that the more valence electrons an element has, the more tightly it holds those electrons. The fewer valence electrons, the less it holds. The element with the highest electronegativity is fluorine, which is up here. It's in group 17. It's the top one. And it has the very highest electronegativity. It has 7 valence electrons, right, because it's in group 17, and it really, 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 really holds on to those electrons. It is virtually impossible to get fluorine to give one up. At the whole opposite end of the spectrum is an element down here called cesium, and its neighbor francium, and I think I have this order backwards now that I look at it, but either way, these are the bottom 2 elements in group 1. Cesium and francium have very, very, very low electronegativity, so up here we're very high electronegativity. So they're really willing to give up their valence electron. They only have 1, they're in group 1. They're like, no problem, we'll easily give that 1 away. It makes us more stable if we have all of our electrons in a lower energy level, so we're happy to get rid of the only one that's hanging out up there. So the pattern that we see here is anything in this corner, let me get another color so it's easier to see, anything in this corner has very low electronegativity, and anything in this corner, well, except for the noble gases, we just ignore them because they don't react with anything and they're just all nice and stable as it is. But anything else in this corner up here by fluorine has a very high electronegativity. So as we go diagonally across the periodic table, electronegativity tends to increase. It gets higher the closer we get to fluorine and lower the closer we get to francium and cesium. So those are the trends and patterns that we are going to focus on in this section. There are quite a few more discussed in your book, but we're going to focus on just these 4. So go ahead and write some clarifying questions for discussion when we talk about this lecture, and write your summary, and I will see you in class. Thank you. And